Assalamualaikum. My name is Muhammad Samsul Sairi bin Saidi. My metric number EC19002. For the introduction, diabetes mellitus is a group of diseases characterized by a high blood glucose level that result the lack of insulin production, or insulin action in the body. According to the International Diabetes Federation (IDF) in 2020, there were 43 million people have diabetes in the world, and 163 people in the Western Pacific region such as Malaysia, China, and Cambodia. This figure is expected to increase to 212 million on 2045. This statistic is driven to an efficient research to conduct in order to increase the prevention, improve method, and ideally to find treatment for type 1 diabetes mellitus patient. Then this study focused on T1DM to regulate the blood glucose level through oxygenous insulin control. In this study, a nonlinear complemental model referred as Hovorka model, which control algorithm is used to information about the behavior of the T1DM patient can be gained to help find a suitable way of administering insulin injection. For the methodology, the block diagram of the closed-loop PID control system for insulin control on blood glucose regulation in type 1 diabetes mellitus (TYDN) represented using Hovorka diabetic model as the withdrawal patient. The insulin input to the withdrawal patient is depending upon the difference between the actual blood glucose concentration from the feedback loop and desired blood glucose concentration from the glucose reference input. Then this error signal is fed to the PID control system to estimate the amount regulating the blood glucose concentration. The mean disturbance for certain duration is also input several times to the Hovorka diabetic model to represent as the blood glucose affecting factor. The PID controller, calculate the insulin delivery based on function of the three term. Proportional term is adjust the insulin delivery in response to the current glucose measure level. Second, integral term adjust insulin delivery according to the area under the curve between measured and target glucose set point. And third, derivative term deliver insulin in response to the rate of change of blood glucose over time.
Our simulation for the insulin delivery control system, which consists focus on the PID controller, using the PID controller, and we should have a two plot, which is the insulin part and the glucose part. So the glucose plot and the insulin plot. So each of this from here at time 5. This is the breakfast, and this is lunch, and this is for dinner. Okay. So let's run the simulation. So this different color is the insulin deciliter per minute, glucose digestion, and glucose milligram. So we have two different another two uh, transfer function, which is the step and the simulation without the PID controller and step. And but we use the PID because we want to know more. We want to dig deep about the PID controller applied in the insulin delivery control system. So thank you. Hi, my name is Muhammad Daniel, aka 194004. Um, Question A01 insulin delivery control system. So we search for PID control. So the set point SP is the target value and process. Variable PV is the measure value that may deviate from the desired value. Hi, my name is Muhammad Daniel, aka 194004. Um, Question A01 insulin delivery control system. So for the calculation, this is my calculation. Actually, so this is my calculation. Uh, so we start with a proportional integral derivative PID. So this is the first thing we need to know, the PID controller, because we search for PID control. So the set point SP is the target value and process. Variable PV is the measure value that may deviate from the desired value. The arrow from the set point is the difference between the is defined as ET is equal to SP minus PV. And discrete with discrete sampling periods and discrete form of the PID equation is needed to approximate the integral of the error and derivative. So it also replaces derivative with discrete sampling periods and discrete form of the PID equation is needed to approximate the integral of the error and derivative. So it also replaces derivative with either a filtered method to approximate the instantaneous slope of the PV. So IMC tuning correlation is the common tuning correlation for PID control is the IMC rules and the Simulink. So the final value we get from the plot graph and we put it into the KP formula, and from the value 3 negative 3.62 gives 63% there. So we calculate that, which is from this one time constant, and tau d is equal to 0 hour and kp is negative 3.62 deciliter micro per minute. And for the discussion, so we apply to our Simulink and blood glucose display and the insulin low limit, high limit, that's all. And oh yeah, the insulin pump too. This the continuous injection person's body. So that's all for
As a conclusion, we can conclude that by this laboratory, we know on how to use and apply the computational technique by using the magnet simulate. Based on the result discussed, it is that in order to retrieve a satisfactory glucose regulation throughout the proportional integral derivative PID control, the parameter setting to work closed loop response of a short rise time, steady state error elimination, overshoot and setting time decrement are required. The PID controller of which a fast response give an optimum control of the glucose regulation because of the integral action can eliminate the steady state error and furthermore can decrease the rise time of the controller transfer function while at the same time the derivative parameter remove any overshoot and shorten the settling time of the controller transfer function.